Have you ever wondered how we actually achieve those mind-blowing high-speed, low-power internet connections? Well, to push the physical limits of data transmission, engineers rely on a pretty fascinating clash of methods. Incredibly fast analytical math versus heavy-duty 3D simulation. Today in this explainer, we're decoding the engineering magic that makes microscopic optical chips and modern internet speeds absolutely possible.
Okay, here's our roadmap for today. We'll start with silicon photonics basics, look at the coupling challenge, unpack our two main tools, analytical math and 3D simulation, compare their data head-to-head, and finally reveal the ultimate design workflow.
All right, let's dive right into this. Section 1, Silicon Photonics Basics. So the core question driving modern tech right now is this. How do we make data transmission exponentially faster while somehow consuming less power? You see, traditional electronics are basically hitting a physical brick wall. Pushing electrons through copper at massive scales generates just way too much heat. And that is exactly why the entire industry has aggressively shifted toward optical chips.
This brings us to silicon photonics. Instead of electrical currents, we're using microscopic highways of light. By building these tiny structures called waveguides, we bypass electrical resistance entirely. We are literally shooting photons directly through perfectly engineered silicon. It's a real game changer.
Moving on to Section 2, the science of light coupling.
Picture this like lanes on a microscopic highway. Let's compare a 700 nanometer waveguide to a 500 nanometer one. The 700 nanometer path has a higher NF, which basically means it hugs the light really tightly, giving us strong optical confinement. But if you shrink that lane down to 500 nanometers, that confinement weakens. The light starts interacting more with the boundaries, and that causes higher propagation loss and a lot more scattering.
Now, what happens when these optical highways get a little too crowded? When waveguides are placed side by side, the light naturally leaks or switches lanes right into the adjacent waveguide. But here's the thing. This isn't a flaw. Precisely controlling this optical leakage is absolutely crucial because it's exactly how engineers build vital components like ring resonators and wavelength filters.
Which brings us to Section 3, Math, the analytical approach.
So how do we predict this leakage? Well, the very first tool engineers reach for is coupled mode theory, or CMT. It's a mathematical model that calculates the electromagnetic field overlap between adjacent waveguides. Now, it assumes ideal, uniform modes. Because it's a theoretical equation, it computes almost instantly. That makes it absolutely perfect for doing rapid parameter sweeps during those early conceptual design phases.
Now, what's really interesting about this slide is, well, first of all, don't let that calculus intimidate you. The absolutely crucial variable to focus on here is K, kappa. This is our coupling coefficient. It's effectively measuring the strength of that lane switch we just talked about. The higher the kappa, the stronger the light leaks into the neighboring waveguide, all based on the geometry and the gap distance.
Next up is Section 4, Simulation, the 3D FTDD method. When basic math just isn't enough, we bring in the heavy artillery. FTD stands for Finite Difference Time Domain. It's a numerical method that solves Maxwell's equations directly in the time domain, but across full 3D structures. So instead of just plugging numbers into an ideal equation, FTD builds a highly realistic, dynamic virtual world so we can see exactly how the light physically behaves as it travels.
You might be wondering, why burn so much computational power on this? Well, it's because 3D FTD captures all those complex realities that 2D analytical math simply ignores. It maps out incredibly realistic field distributions, it fully accounts for waveguide curvature, like when light traverses a 50 micrometer radius bend, and it factors in real-world scattering losses.
Time for a head-to-head showdown in Section 5, Analytical versus FTTD results.
And this brilliantly illustrates the difference between theory and reality. As the gap distance between our two waveguides widens from 200 to 400 nanometers, that coupling coefficient kappa drops exponentially. But take a close look at the slight numerical discrepancy there. At a tight 200 nanometer gap, the math model predicts a kappa of roughly 0.38, while the 3D FTD simulation shows it slightly lower, at around 0.35.
So why is the 3D FTT data slightly lower? It's kind of like a physics mystery. Actually, scratch that, it's not really a mystery, it's just the messy reality of physics. The math predicted a higher coupling strength because it assumed an ideal, perfectly straight path. It completely missed the real-world losses caused by the waveguide actually bending. The 3D simulation, however, caught all those phenomena, the bending losses, the curvature phase mismatch, and the modal dispersion, which gives us a much more highly accurate result.
Let's wrap this up with Section 6, the ultimate design workflow.
As you can see, the ultimate workflow isn't about crowning one method the winner. It's a really powerful two-step synergy. Step 1. You use your analytical math for rapid parameter sweeps. This lets you instantly test hundreds of gap widths and geometries to find your ideal ballpark. Step 2. You take that narrowed-down design and run it through high-fidelity validation with 3D FTDT. Combining the blistering speed of math with the uncompromising accuracy of 3D simulation ensures the chip is going to work perfectly when it's finally manufactured.
But this leaves us with a pretty fascinating, provocative thought. As we demand more speed and even lower power, what exactly happens when these photonic chips become so incredibly densely packed that even our absolute best 3D simulations struggle to keep up with the quantum effects of light? It's wild to think about. As we push toward the very limits of nanoscale engineering, our digital tools are going to have to evolve just as fast as the chips themselves. Thank you so much for joining me for this explainer, and keep questioning the science that's driving our connected future.